Hi, I'm Kate Trotter. I'm a graduate student at Oregon State University, and I'm currently working with E Lambda on a free-space optical communication system. So what I plan on showing you today are the improvements we've made in the system, particularly in beam forming and beam steering. What these results will show is that we're able to get a high-speed lock-on within a matter of a second. Here we are at the beam forming beam steering setup. What you can see is a VCSEL diode coupled into two lenses that collimate the beam down to a size of about 4 millimeters. That 4 millimeter beam then strikes the surface of a MEMS-based deformable mirror. This is where the term beam forming comes in. This mirror electrostatically actuates, which allows for control of the divergence angle. That control of the divergence angle allows for control of the size of the beam at a known distance. That beam then goes into the Galvo mirror, which allows for the beam steering component of it in the field of view. That beam then goes downrange to a retroreflector and comes back, striking the photodiode and going to a DAC. Over here at a distance of 3 meters from the transmitter, we can see our receiver. What you see is a photodiode wrapped around by a retroreflector in a toroidal shape. When the field of view is scanned, the light will bounce off the retroreflector and go exactly back to the source, providing detailed data on where the target is based off angular location. When the Galvo mirror scans the field of view, it does so utilizing a hexagonal raster pattern. Our system blends the requirements of accuracy and time by utilizing a three-step process. This process can be broken up into three major chunks, the first of which being a large area, low angular resolution scan. As you can see in the image provided, we scan over 20 degrees in the X direction and 20 degrees in the Y direction. What you can see is a normalized reflection value, the key of which is the yellow value with a red dot on it. The yellow represents a high reflection value, where the red represents the fact that we've located and chosen to position there. Once the user has been located, we then zoom in by using a 2 degrees by 2 degrees field of view, and then drop the angular resolution down so we can get a much higher resolution view of the target. Looking at the target, we're able to establish the donut-like toroidal shape. Using this data, we can then do a convolution with a kernel fit to the same general shape. That provides us with the general location of the center of this target. Once the center of the donut shape has been roughly found, we then go down one more time to the third step. This third step utilizes a 0.3 by 0.3 viewing angle. What we then do is search for every data point below the 30th percentile, group them together, and then find the center of that, as seen in the image. The low reflection value in the image included is indicative of the whole of the retroreflector. That would be the center of the toroidal shape. This dark patch is representative of approximately 5 millimeters. As you can tell by the placement directly in the center, we are able to get a very high resolution, high quality lock with the beam. On the left you can see our oscilloscope depicting the quality of the beam lock through the means of an eye diagram. On the right you'll see our photodiode with receiver. What you can see is that the first scan has successfully achieved a high quality eye diagram. We will now move the receiver such that the beam is no longer incident to the photodiode. We will then do a second scan to try and get another high quality eye diagram. As you can see, very successful lock has occurred